Mathematics. Abstract, immutable, and as old as civilization. It's the language we use to describe and understand the world around us. From artificial intelligence and cryptography to engineering and economics, mathematics gives us the tools to predict, model, and design the increasingly complex world we live in. To progress the state of the art, every 4 years sees mathematicians from all over the world come together for one of the world's biggest mathematical events. Now, here in Valencia, Spain, we're ready to join the thousands of delegates attending the 2019 International Congress on Industrial and Applied Mathematics. It's ICIAM 2019, and we're ICIAM TV. Welcome back to another day at ICIAM 2019, another day to explore the fascinating work that's on offer in applied mathematics here in Valencia. Today is Industry Day, focusing on the impact that mathematics can have on businesses worldwide. And our theme is engineering and technology. Designing, building and maintaining an efficient and effective product, from buildings to devices, is at the heart of industry. But as mathematicians know, the more complex the product, the bigger the challenge. Without mathematics, buildings wouldn't stand and engines wouldn't operate. At the same time, it's mathematics that can drive technology forward through a better, more detailed description of the systems at play, in anything from hydrodynamics to electromagnetism.
In the sale of our cell phone, and such as when the aircraft go back into the Earth, this number is deviated from zero. So in this case, we have to describe it using Boltzmann equation.
This to me was always a great challenge, computing things in the complex plane, because the complex plane often tells you more about a function than just looking at it on the real axis.
Employer to make blunder, work slowly, don't get too much in administration of science, just enjoy it. Or do something else.
The applications that mathematics can have on industry and on our understanding of the environment are boundless. And that is exactly what our next guest, Professor Alfredo Bermudez, will be talking about in his lecture entitled Some Case Studies in Environmental and Industrial Mathematics. Alfredo, thank you for joining us.
Thank you.
Could we start by talking about why you're bringing 4 very different case studies to ICIAM 2019?
I try to emphasize some things, in particular the fact that mathematics is quite transversal. And the other thing I like to emphasize is the fact that industrial or environmental mathematics, that is true applied mathematics, are also interesting from the, let's say, academic point of view. So the outcome is not only the industrial outcome, the demand from the companies, but also articles, papers, that is very important in the career of a researcher.
So maybe we could talk about those 4 different case studies. The first one is environmental fluid mechanics.
In environmental fluid mechanics, I try to simulate the evolution of the pollution in a sea area in order to optimize the wastewater treatment systems.
And what about in the gas transportation network?
Well, simulation and optimization of gas transportation network is an important issue in the field of energy. The idea is that you have some compression stations in the network. These compression stations are needed to push the gas because the gas is dropped in pressure because of friction against walls. So the idea is how to manage the network in order to reduce the cost.
And I think the third case study that you looked at was testing of car parts using magnetic nanoparticles. What were you looking for there?
In this case, it's a demand from a company manufacturing car parts, in particular crankshafts. And in order to determine the existence of some brakes, surface brakes, one can use the so-called magnetic particle inspection to simulate the magnetization and demagnetization of this piece by using mathematical models coming from Maxwell equation in electromagnetism.
The 4 case studies that you are discussing are all very different from each other. Do they have anything in common?
Yes, in fact, all have in common the fact that numerical simulation is done by using partial differential equations and numerical methods to solve them. And this allows us to go to different physical or engineering areas.
The case studies have really shown how diverse applied mathematics can be. What advice would you give to any of the young mathematicians that are here, the young researchers trying to pick an area to focus on?
You also need to know other disciplines. You need to know fluid mechanics, electromagnetism, chemistry, sometimes something in medicine. So the interesting thing is mixture, this mix between mathematics and other disciplines. There is a field of research and application very important.
Well, Alfredo, thank you so much for joining us. It's been great to talk to you.
Thank you. Thank you.
All kinds of industry benefiting there from advanced mathematics. Next, with close collaboration with industry and government support, we'll be taking a look at the Basque Centre for Applied Mathematics. But first, let's take a look at the full list of featured organisations on ICIAM TV.
The Basque Center for Applied Mathematics, BICAM, is a world-class interdisciplinary research center in the area of applied mathematics. It was founded in 2008 by the Basque government as a node of the Basque Excellent Research Center in the Basque Country. Our goals are to do high-quality research, to train new researchers, to attract talented scientists, and of course the development of new mathematics. The center is divided in 5 research areas, and these areas are subdivided in research lines. Mathematical modeling with multidisciplinary application, mathematical physics, analysis of partial differential equations, computational mathematics, and finally data science and artificial intelligence. BICAM is a really inspiring place. It has very young people, 25 different nationalities, a group of 100 enthusiastic researchers which cover a really broad area of the mathematics in such a way that it doesn't matter what you ask for, there is always an expert in the center who can answer your question or at least give an advice on your question.
What makes the Basque Center for Applied Mathematics a reference center at the international level in applied mathematics is first its excellent quality. It has very good researchers from many countries, also a very good management, the inside, outside, so there is very good collaboration between different research lines within the center, and they have also interdisciplinary research with other centers, technological or research centers. They work on real problems coming from the society of industry, so they have contracts with companies, hospitals, etc. They are one of the 2 centers in Spain that have a Severo Ochoa grant in mathematics, and they are the only one in applied mathematics having a Severo Ochoa grant. They have 2 J.A.C grants, several Ramon Cajal grants, Marie Curie, so they are really very well positioned, both in the Spanish landscape and the international one.
The organization of BICAM has 2 different possibilities. One is horizontal, which are the different areas, and then the other one is vertical, which are the different platforms. The bottom platform is what we call the core in applied math. The upper platform is what we want to feel that our knowledge is transferred to the society, and in between what we have to do is computations and simulations of what we want to apply. We do believe that to do good research in applied math is based on a fundamental top research in basic mathematics with a special emphasis in applied math. So we really try to push the frontiers of mathematics as far as possible.
The main research objective of the computational mathematics area is on the development of new mathematical models and numerical algorithms to describe complex physical processes. And this is practically realized by means of computer simulation, and in particular the massive use of high-performance computing. Among the computational technologies which are developed in this area, I would mention advances in grid-based and meshless techniques for the solution of partial differential equations, such as the popular finite elements, finite volume scheme, or smooth particle aerodynamics, but also the development of new stochastic coarse graining techniques for the description of non-continuum mesoscopic problems. So from one hand, we want to use computational technologies already developed in our centers to improve our understanding of physical processes, in particular provide explanation for physical observation or even predicting new phenomena. And on the other hand, we apply actually our techniques to challenging problems in industries, to optimize design or processes in industrial settings by using tailored software solutions.
BECAM's Knowledge Transfer Unit is a platform to develop mathematical solutions for the industry. We develop collaborations with industry in different ways, such as joint positions, strategic partnerships, research projects, training courses, or organizing dissemination activities. For example, the European Study Group with Industry is a platform in which young talented scientists work together trying to solve real-life problems for companies, such as non-renewable energies, trying to predict and analyze stock prices, developing numerical algorithms for cardiac radiofrequency, or numerical methods using computational fluid dynamics for advanced additive manufacturing. Recently, we have been working in exciting topics like sports science and sports medicine in development algorithms to try to predict sports injuries.
BECAM is a very attractive place for young researchers for a number of reasons. One of them, which is fundamental, is the stable environment and the stable funding that people find. The other is the synergy that's generated among the young researchers, which really propels them and multiplies the effect of their presence and the excitement. Classical and pure math is thriving. Many important long-standing conjectures are being solved, new theories are being developed, new problems arise. But besides that, the interactions with applied math, which are so crucial for our society, continue to develop, and this will be another source of interesting pure mathematical problems for years to come.
I would recommend people to come to BECAM since we know that there are quite a lot of opportunities, being a PhD student, job offers, but also to visit the center to collaborate with people for some months. Bilbao and the Basque country in general is a great place. We really invite you to come here.
One thing for me very important here is that the young people, because you have many references to the future. I think it's a good thing because you can have perspective about the future here in BECAM.
At the Basque Center for Applied Mathematics, we have a dream, and our dream is to construct the necessary mathematics to improve the social welfare. We'd like to lead the development of these mathematics that can contribute to improve our society. And we count with all of you. We'd like to write together the mathematics of the future.
Now he's been doing a wonderful job meeting some of mathematics' top minds. Now it's time to go back to Professor Ortegón as he catches up with Professor Weideman on the dynamics of complex singularities of nonlinear PDEs.
Professor Weideman, thank you for joining us. What are the main topics you've been working on?
Well, I started my research back in 1986 with computation of nonlinear waves, My thesis topic and my first paper was on the computation of the nonlinear Schrödinger equation. After that, I switched fields, not very far, it was always numerical mathematics. I went into spectral methods for differential equations, methods for computation of integral transforms, maybe the Laplace transform, for example. But then lately I've been turning full circle with my research, and at this conference I'll be back to the world of nonlinear waves, now with a different twist by looking at what these waves do in the complex plane.
Can you give us an outline of your talk, a more detailed outline?
I thought I would present for this talk a few of the historically important differential equations, but look at them, what they do in the complex plane, and particularly how to compute their behavior in the complex plane accurately. This to me was always a great challenge, computing things in the complex plane, because the complex plane often tells you more about a function than just looking at it on the real axis. I mean, the favorite quote of mine in mathematics is by Painlevé that says, often the truth in the real domain goes through the complex plane. The shortest path between two truths in the real domain goes through the complex plane. If you look at these solutions, which are real, defined on the real domain, but if you take them into the complex plane, often they reveal features that you may not have seen before.
Okay, so you've come from South Africa. Is there any program to capture young talent in your country?
It's always a problem capturing young talent, but there are several initiatives. If I could speak broader than just South Africa, there is this Institute for African Mathematical Sciences called AIMS, African Institute of Mathematical Sciences in Cape Town, which draws a young talent from everywhere in Africa, put them all in one place, invite excellent speakers from abroad, take them through a structured master's program, and by the end of that they are ready for competing with the best the world has to offer.
I've just learned that you are the main responsible of the organization of a conference that is held in South Africa.
We have our little conference called SANM, South African Numerical and Applied Mathematics. It has been going for 44 years now. That's quite a conference. But yeah, we're very proud of it. It's a small conference, just 3 days. We're a small community, maybe 60 people, but we get some of the top speakers from elsewhere in the world. We've had some ICIAM presidents like Nick Trefethen and Nick ICIAM giving plenary talks. Next year it is Annie Kuyt from University of Antwerp in Belgium and Randy Levesque of Washington University. So we're looking forward, and we invite everyone to show up and come and join our conference. We also have a bigger mathematical association in South Africa called SAMS, and I believe that has now become part of ICIAM as of this year.
So thank you very much, Professor Weideman. Thank you for joining us.
Thank you.
Fascinating stuff there from Professor Weideman. Now let's take a look at the Berkeley National Laboratory, where mathematics is driving scientific technology, from synchrotron light sources to particle accelerators.
In the scientific community, there's an ever-increasing emphasis on looking at problems that are of increased complexity. That increased complexity can come from having additional phenomenon, needing to look at a broader range of scales, or changing the kind of question that you need to ask. The reliance on computation is increasing over time, and our goal is to facilitate that. That involves helping figure out what the right system of equations to look at are, understanding the properties of those equations, developing discretizations of those equations that are suitable for simulating on a computer, figuring out how to implement that on a computer, and analyzing the data that comes out of those simulations. So one of the nice things about Berkeley Lab is the ability to look across that entire spectrum for a single problem.
We're charged by the Department of Energy to work with DOE facilities, and these in particular include the synchrotron light sources. And there's one at LBL called the Advanced Light Source.
A lot of the work that we've done in the past has been focused on simulating different phenomena. A recent new direction is looking at experimental data. We need new mathematics to be able to understand the relationship between what's actually measured and what scientists actually want to know.
CAMERA has multiple projects at work. They range from tychography to fast tomographic reconstruction to image processing using convolutional neural nets, to ways to automate experiments, to do inverse reconstructions in things like single particle imaging and fluctuation scattering. The sky's the limit.
One of the problems that we're having right now is analyzing vast amount of data. But the methods that TESS is, for instance, developing might be able to give us some relief of this tsunami of data that comes at us.
Yeah, so one thing that I work on is developing deep learning algorithms, which are a particular type of machine learning. So these are programs that you can think of that have sort of parameters that need to be fitted to data. But if you imbue a lot of context and prior knowledge into these algorithms, not too much so that it's restrictive, what you can do is that you can fit very accurate models with minimal training data, but yet apply it very quickly and very easily to large, vast amount of data that are coming out of these new facilities.
The key distinguishing factor of LBL is that you're allowed to put together big teams. We face these really large, challenging problems. They're very difficult for a single investigator to pursue, but at LBL we can assemble a team and draw together all the different kinds of expertise you need and use that to attack these big, outstanding challenge problems.
The big question we're working on is how to make particle accelerators much smaller, much cheaper. The new type of particle accelerators, that's called the plasma, they require a lot more computation. There's very small beams that propagate in this very long structure. That means a lot of what's called time step, to compute the evolution. It's really key to revisit the algorithm, whether it's reusing some of the algorithm that now become adapted again to the architecture that we have to work with now, or whether it's coming up with really new algorithms that are the best for this type of new architectures.
The study of mesoscale science is becoming one of the really interesting new areas. It's fascinating to look at this and see all the new kinds of behaviors that come out and figure out how to solve those things computationally.
These systems operate on a set of energy scales where thermal fluctuations play a large role. So we have to account for that by introducing some stochasticity into the dynamics we're evolving. And in this way we can understand the impact of microscopic dynamics, fluctuations of proteins, if we're looking at some biological system, on the larger scale dynamics of the system.
Our role is to develop, methodologies for dealing with the kind of issues that Katie just described. So, for example, we're working on a code to simulate electrolyte solutions. And in that case, we're treating the water molecules as a continuum to which we add thermal fluctuations with a method known as fluctuating hydrodynamics. But we're treating the ion species themselves as discrete particles. So this is an example of the kind of mixing of different scales.
Berkeley Lab is an excellent place for someone to come at the beginning of their career. When they come to Berkeley Lab as a postdoc, they get to participate in this larger team science. And for many of them, it's a real eye-opener. And it's just a different way to do business that's very exciting.
My favorite part is getting all these teams to actually work together. The process of getting good applied mathematics to be relevant to a problem requires months. People talk with different languages, there are different cultures, there's different metrics of success involved. And watching them all focus together has really been a very rewarding part.
Welcome to the ICIAM TV classroom, where we're going to be talking about kinetic equation. It's an essential tool in depicting phenomena in physics, but in its various forms and over the years, it's revealed a number of limitations. Well, here to discuss his work in the field, I'm delighted to be joined by Professor Ruo Li. Ruo, thank you so much for joining us. What are the applications of kinetic equation and what makes it so challenging?
Yes, since the Kinetic Equation, there is a function with a lot of variables. So it's extremely difficult to carry out any numeric studies. Yeah, so our method is trying to remove some of the variables to make it a much more simpler case. We know for 60 years that the gross moment method can never give correct physical prediction in the history. The major difficulty is the nature of the hyperbolicity. My major discovery in this direction is trying to resolve this problem completely.
How has the field grown since the 19th century Boltzmann equation?
Yeah, since we are trying to describe the fluids in some extreme region, that's the most important thing in physics. If we want to study a lot of particles in a volume, so just like this in a volume, and we have a lot of particles in it. So the particles, they are moving and interact each other. So we assume that this thing to be a length L, and so there is a so-called mean free path. If this length is an L, so the most important parameter for this system is the ratio between this L and this L. So it's called the closed number, and this is this ratio. In our everyday circumstances, such as the atmosphere in this room, this number is very, very small. So we can directly use the microscopic hydrodynamics to resolve the atmosphere in this room. But in the cell of our cell phone, and such as when the aircraft go back into the Earth, this number is deviated from zero. So in this case, we have to describe it using Boltzmann equation.
Can you talk us a little bit further through your recent discovery?
For the Boltzmann equation, and we know that it's a very high dimensional case, and so gross moment method is trying to reduce a high dimensional equation to a low dimensional one. With our work, for this closed number, if it's going to zero, and we can have the classical Euler or Navier-Stokes equation to resolve it. For this is going to 1. This one is very big since the particles will travel along the room. So the Boltzmann equation can describe the problem for this thing to about -2 to 1. So in this procedure, we can always describe it by Boltzmann equation, but we need to have some intermediate model between this Euler and Boltzmann to model the system around this region.
And that's the Grad's moment method?
That's Grad's moment method. And we can have this Grad's moment method here. In the last 60 years, Grad's moment method is always be collected in a textbook. There will be ending with such words. This system is so important. It has never given us correct physical predictions. So the problem is the lack of the hyperbolicity. Our work is to make the system to be hyperbolic.
Thank you so much for talking us through your important work, Ruo. Thank you for joining us.
Thank you.
Now let's meet a group that's focusing on solving engineering and technological problems. The Heidelberg Collaboratory for Industrial Optimization is working with partners across the board in the aerospace, automotive and healthcare industries.
The new Mathematicon building at Heidelberg University is the home of the Heidelberg Collaboratory for Industrial Optimization, or HCO, and its mother institution, the Interdisciplinary Center for Scientific Computing, or IWR. Scientists at the HCO work on model-based simulation and optimization, which have become technologies crucial for the development of better products and processes in industry. While the problems come from fields as diverse as the automotive industry or chemical and pharmaceutical engineering, the necessary mathematical solution methods and tools are based on the same principles.
The HCO is a consortium of 8 senior and junior research groups of the IWR. It has about 50 scientists with ample expertise and experience in optimization and optimal control of industrial processes in a broad sense. With this, we are a part of the technology transfer strategy of Heidelberg University. On the optimization side, HCO covers a wide range of methods, from highly nonlinear and large-scale systems to mixed integer optimization and optimal control, and to model predictive optimal control in real time. On the process side, the expertise ranges from switched ordinary and differential algebraic equation systems to, for instance, reactive flows with partial differential equations in porous media.
The success stories of HCO include a wide range of industrial partners across many domains of application and business areas. This includes aerospace engineering, air traffic control, energy optimal control of trains and heavy-duty trucks, robotics and mechanical engineering in general, and power engineering in particular for the challenges of the energy transition. We also work on unsolved problems in medicine and healthcare. The chemical company BASF was so convinced about the potential of the newly developed optimum experimental design methods for differential equation models that they sponsored a whole research group at IWR with 3 full-time scientists for 6 years just to further develop the technology. BASF says that they save up to 80% of the experimental costs with these new methods, and they often have unexpected results and may lead to changes in investment decisions which are worth in the million euros range.
One of the most striking success stories is the collaboration with Daimler AG. We developed an extremely fast nonlinear model predictive control method that can handle discrete decisions such as gears, and that is within milliseconds.
Heavy-duty trucks such as the Mercedes-Benz Actros are an important factor in long-distance transportation. And so Daimler developed a predictive cruise control system that minimizes energy consumption by choosing the right fuel, optimal gear and acceleration. The new mixed integer optimization techniques developed at Heidelberg allow to compute such optimal controls. They were used to compute optimal strategies for various roads, traffic scenarios and trip durations. Predictive powertrain control shows fuel savings up to 5%. Daimler AG therefore brought predictive powertrain control into market with great success and thanks all members of the HCO.
We're here at Heidelberg University Hospital in Motion Analysis Lab. We are monitoring here patients with neuromuscular and orthopedic disorders, both for clinical service and also for research. In the research, we are much interested in how you optimize gait by speed, by energy. This is also subject to many research projects in close collaboration with the HCO at Heidelberg University, where they're interested in exactly this math behind gait.
The research at HCO also leads to widely applicable optimization software, which is a crucial venture for a university institution. We are very proud of having recently won a pioneering scientific computing sustainable software lab endowed by the Carl Zeiss Foundation.
Everybody can freely download our real-time optimizer QPOasis. It made us proud when we learned from ABB that this software package was successfully deployed in industrial reality at 2 gas facilities in Norway. There, QPOasis helped to continuously re-optimize every millisecond the operation of 2 42-megawatt gas compressors. The new mathematics successfully protected the compressor operation during voltage dips, for which failure can mean financial losses that range into the hundreds of millions US dollars per year.
Significant savings are also realized by computer tomography scans of solid objects with methods developed in Heidelberg.
In order to adopt a new non-destructive TT-based technique as industry standard, a quality inspection has to be fast. Our method reduces the time it takes to scan industrial objects by using few measurements only. New mathematical tools from compressive sensing allow us to aptly calibrate the sensors before deployment. Reconstruction of correct objects is guaranteed, while defective ones can be filtered out directly.
In space engineering, one serious problem is that occasionally satellites are placed in the wrong initial orbit due to malfunctioning of the launcher. This initial orbit must be then determined very fast to allow for correction maneuvers. Together with the European Space Agency, we have developed a very fast, reliable and robust orbit determination method based on our multiple shooting method. This method successfully passed its practical test when 2 Galileo satellites were mislaunched 4 years ago.
At IWR, we organize, of course, a lot of workshops. In order to identify the really hot topics important for industry, we have successfully established the brand of so-called challenge workshops, which is now accepted as a best practice. Most recent examples are the 2 workshops on model-based optimization for the pharmaceutical industry and on the industrial paradigm of digital twins. The HCO, the Heidelberg Collaboratory for Industrial Optimization, brings together researchers from industry and academia to create synergies and to establish strategic research collaborations with industrial partners, which go beyond short-term individual contract, in order to master the industrial challenges of today and of the next decade.
Now, this year's Maxwell Prize has been awarded to Claude Bardos, a mathematician who's had a major influence on generations of mathematicians for his wide-ranging work, and I'm delighted to say he joins us now. Claude, thank you for joining us. First of all, many congratulations on the prize. How did you get started in mathematics?
Okay, that's a long story. My grandparents helped a lot a guy who survived the war. We were all Jewish. But this guy started in mathematics before the war. Several of his friends went back, started to work with Dassault Aviation, where they made the plane, the fighter, the Ortegón by that time. So they hired him as a very junior engineer. He was frustrated not to do mathematics. So he started to teach me mathematics when I went to see my grandparents at the age of 12. And maybe it's a reason why I like fluid mechanics, I like applied mathematics connection with industry and so on. That's it.
To look at some elements of your work, what is it about partial differential equations that you find so interesting and exciting?
It's really at the cornerstone, at the crossroad of several domains, both of theory and of practical example in life. It became essential at the time of the appearance of quantum mechanics. But in the meantime, later people I mean like Peter Lax and Faddeev, found that it was closely related to the Riemann hypothesis, which described the behavior of number theory. So someone working in PDE is at the middle of all that, and I liked that.
How have you seen this field develop over your career? Has it changed much?
I think it got a lot of maturity, trying to find what are the frontiers of application, what could be easily done, what are still the challenging problems.
What has made you the most proud over your career?
Hilbert mentioned using the idea of Boltzmann to derive a mathematical formulation of fluid mechanics from the first principle and from the hypothesis that the atom exists and they interact. And it turns out that to make progress, to go from this idea to mathematics, when you can introduce number instead of ideas and quantify this number, and that was done by 2 people, which are Joe Keller and Larsen. And I was aware of their work, and I told to students we should jump on that to try to go on on the Hilbert problem and try to make progress on his program. And turns out that we made a kind of roadmap. I think I am responsible for the roadmap, but which end up with very difficult issues, which were not solved by me, but by a former student with François Gols, and one of his students who is very well known, who is Lord Saint-Raymond. And I did stop to work on the problem when it became too technical, too difficult for me.
You just spoke about some of your students, but you've had a major influence on generations of mathematicians. You must feel very proud about that.
Definitely, that's one thing. It's what I told you exactly. I'm proud of what I did because they did the work. It's not me. You can just say that.
Just to finish, we have there are lots of young mathematicians here at ICIAM 2019. What advice would you give to young mathematicians starting their careers?
Don't worry that you make blunder, work slowly, don't get too much in administration of science, just enjoy it, or do something else.
Thank you so much for joining us, Claude. It's been really fascinating to hear from you. And once again, many congratulations. As well as connecting mathematicians with the industries that really need them, an exciting part of ICIAM is its outreach efforts. And central to that is the public lecture. I've been down to the lecture venue to find out more. Normally home to ballet and opera, this week the Palais de les Arts will be hosting a different kind of event. As renowned mathematician Victor Pérez-García presents to mathematicians and non-mathematicians alike, asking the question, can mathematics help in the war against disease? Victor, thank you so much for joining us.
You're welcome.
Perhaps we could start by explaining how, as a mathematician, you got into biology.
Well, you know, I worked on different kind of problems some time ago. 10 years ago, I was working on quantum systems, mathematical modeling of the system, mathematical physics, and so on. But sometimes I felt that it was too far from real world, and I started thinking that whether I could do something more useful to people. And somehow we were exploring what to do, and we found an opportunity on mathematics and oncology, and from there to other problems in medicine.
And at the time, how common was it for a mathematician to work with the life sciences?
You know, it's now quite common to work on mathematical biology problems. More typically, this means getting a model that has been written for a biological system and doing some kind of mathematical analysis with it. What's not that common, and I think it's not that common still, is working head-to-head with medical doctors. So getting the problems directly from them, getting data, and trying to provide answers that are useful for them and not only scientifically interesting.
Well, your lecture will be taking place in the auditorium. Shall we go and have a look at it?
Okay, yeah.
So, Victor, we're here in the magnificent auditorium where your lecture will be taking place. What's the focus of your lecture going to be?
Well, I'm going to focus on trying to show to the audience what is the role that mathematics can play in medicine. It will be general talk in the first part, and then I will focus on three particular examples from oncology where I think some success has been achieved, in the sense that something that was born as a mathematical equation and mathematical concepts and ideas has moved out through the development process towards products or things that are testing in clinical scenarios.
And how can maths help in the fight against disease?
You know, there are many ways in which we can help us applied mathematicians in the fight against disease, and one of them is generating hypotheses. We try to understand the biology, we put some, or at least essential biological rules into mathematical models, and then we analyze the models, and we can find things in the model. We can do many experiments in the model that we can do with real patients. And then these models can suggest ideas that we can go back and test in animal models, in vitro experiments, and then finally maybe in patients if they work.
Well, this is a fantastic venue for that lecture. Should we go and have a look at the balcony and see a little bit more of it?
Yep.
So, Victor, from here we get a fabulous view over Valencia. How much of your work is involved with engaging with the public?
You know, we engage with the public from time to time. We think this is very important. They support our research through universities, through research projects and so on. And this is why I think it's important to give them back and to make them feel that this support is important and somehow this is relevant for them.
And what would you like them to leave your lecture with tomorrow? Would you like to inspire them?
Yeah, I would really like them to feel that mathematics is somehow important, so that we are not people that are somehow hidden in our offices thinking very strange things, but somehow what we do can get back to society and can help them living better lives and taking care of their health. That is one of the most important things we have.
And what would you say in a nutshell, what inspires you?
Well, for me it's very inspiring the fact that we can be useful, because sometimes when you do mathematics you feel like you are doing something that is difficult but it's kind of useless. Maybe someone will use that maybe in 100 years, but this kind of mathematics has a very straightforward application. So for us it's very inspiring to know that we are being useful to others.
Well, Victor, thank you so much. It's been great to talk with you. We really wish you every success with the lecture.
Thank you.
Professor Pérez-García there, showing us that mathematics has a far broader reach than just physics and engineering. Well, that's the end of another day here at ICIAM 2019, and we've really enjoyed exploring the role that maths has to play in engineering and technology. Tomorrow we'll be looking at computing under our theme Big Data and AI. So make sure that you catch our final show online, in your hotel rooms, and also here at Congress. Until then, bye-bye.